Okay, so here's the bonus questions for this round. Number 7 is the nerve action potential, and hopefully I can insert a little video that I made that will help with the calculations. But we'll do it again just for emphasis. So you should, read this, and this tells you about what's happening and how many channels are open at rest and peak and things that are going on with this, each one of these. And so most of the time that's summarized in a table. So here's the table, and we see the concentration in the intracellular and extracellular fluid of X plus, and then the percent permeability at rest, peak, and hyperpolarization, and then it gives the equilibrium potential. You don't always get the equilibrium potential sign, but in this problem you do. It's easy to figure out by looking at what happens on the inside of the cell based on the concentration of the different ions in the intra and extracellular fluid. In the case of X plus, it's a cation, so it's positive. It's highest inside, lower outside, so 120 inside, 10 outside. It will diffuse out of the cell. As it diffuses out of the cell will become more negative. So the equilibrium potential sign should be negative, and in fact it is. It's given here. You are never going to have a situation where the equilibrium potential sign is the same for both ions. So if we know this is negative, we're going to assume the other one's positive, but you should calculate to make sure that you haven't screwed up. So here's also a cation, which is interesting. And you say, how can it have an equilibrium potential sign that's opposite when it's the same charge of the ion? Well, it depends on what the concentration difference is across the membrane. So for O plus, the intracellular fluid is 7, the extracellular fluid is 70. So the concentration is higher on the outside. If I open a channel, O plus diffuses into the cell. It's positive. It'll make the cell more positive, so its equilibrium potential sign should be positive. Now, you don't have to figure out the equilibrium potential numbers, the magnitude. It's figured out by the Nernst equation, and we don't know, we're not responsible for knowing the Nernst equation for humans, let alone, some different organism, right? So you're always going to have to be given that number there. So I mentioned this in that video. What you want to know is what the resting membrane potential is, and that's the contribution of one ion plus the contribution of the other ion. And how do you figure out the contribution of the ion? You're going to use this formula right here. This is the most important formula for this. The equilibrium potential times the relative permeability percent. So where do we get those numbers? We get those from the table above, right? So for X plus, the equilibrium potential is given as minus 100, and the percent permeability for rest is 95%. Now you have to put that in a decimal form. So to get rid of the percent, you divide by 100. So 95 divided by 100 is 0.95. So all you have to do is replace the values with the values from the table. Minus 100 times 0.95. That's easy. You don't even need a calculator for that. That's minus 95. You'll have to add the contribution of O plus. It's the exact same equation. Notice exactly the same, but we have to use different numbers from the table. So the equilibrium potential for O plus is plus 100. You see it up here. The percent permeability is 0.05. And this is, again, a place of caution. A lot of students are going to say, oh, it's 5.5%, right? So 0.5. It's not 0.5, it's 0.05 because you got to divide by 100. So 5% divided by 100 to get rid of the percent is 0.05. The other good check is add those two numbers together. And if you did mess it up, right, you had 0.95 and this says 0.5, should add to 1, that would add up to 1.45. You go, wait a minute, I screwed up. Oh yeah, it's 0.05, not 0.5. So then you do that math, plus 100 times 0.05 is positive 5. And then you just add the two contributions together. So minus 95 plus 0.05 is minus 90 millivolts. Okay. And then I like to do the other ones right away because it's the same formula. The only thing that changes is the percent permeability. So for peak, I just come up here and use 10% and 90%. And for hyperpolarization, I use 98 and 2. So here's the peak. 0.1 times minus 100 is minus 10. 0.9 times positive 100 is positive 90. Add them together, and that's positive 80. And then down here, from the table, I have 98%. The equilibrium potentials don't change, right? They're the same. So 0.98 times minus 100 is minus 98. 0.02, 2%, 0.02 times positive 100 is positive 2. So together they add up to minus 96 millivolts. Okay? So my peak potential, my hyperpolarization, and my rest have been done. Right? So rest is minus 90 millivolts, peak is plus 80 millivolts, and hyperpolarization, it doesn't occur in every problem, but if you get the math, if you know what the numbers are, then you should calculate it, right? And that's 96, right? So minus 96 millivolts. Remember to keep the signs, right? Plus and minus, so you don't accidentally drop a sign. Then it asks you to use the numbers that we had before to figure out the threshold. First thing you do is figure out the total excursion by taking the absolute value of rest and peak. So we get minus 90 plus 80. You ignore the signs, and that's 170 millivolts. You determine the threshold. Again, the threshold percentage. Come up here, and this is the key statement right here. I'll highlight it. This will cause a change in the action potential until at exactly 1/10 of the difference between the resting membrane potential and the maximum change of the action potential. So basically, this gives you the definition of the threshold. So that's 10%. So we take the 10% that was given, right, and then multiply it by the total excursion. So 170 times 10% is 17. And then you take 17 and add it to, in this case, the minus 90 because you're going towards 0. If you started out in a positive membrane potential, then you would subtract it and go negative. But here we add it because of that. So you always want to, the threshold should be between rest and 0. Okay, so the threshold has to be between rest and 0. That's a good little rule of thumb in terms of that. You know, the other point is there's nothing magical about being negative membrane potential at rest. Right? Humans are about minus 70 at rest. There's nothing magical about it. What's magical is that we're polarized. We're away from 0. And had we had slightly different ions or slightly different charges on different ions, then we could have easily evolved to have a positive 70 millivolt resting membrane potential. But we didn't. But there's nothing magical about the negative. So you could have situations where we're positive. To be honest, there are none that we know of, at least scientifically, but it's theoretically possible. So once you get that number, minus 73 millivolts is my threshold. Here's a nice summary here. And then you can just kind of connect the points and figure out what the action potential looks like here in the drawing. So we just put in minus 90, minus 73 for threshold, peak at positive 80, and then my hyperpolarization at minus 96, and kind of nice drawing. And surprisingly, or maybe not surprisingly, it looks a lot like our action potential. Slightly different numbers, but really the overall look, right, is pretty much the same. It looks a lot like our action potential. So that's kind of the point of that question. So that was that one. I had not planned on doing the extra 2 group problems on the bonus number 7 and 8, but I figure I'll see how this works and test it out. So number 7 asks about the action potential. And so we have to calculate what's going on with the action potential. So let's take a look at the information that's given. First of all, we have two ions. We have an X positive and an O positive. So they're both cations. In the ICF, the concentration of X plus is 120 millimoles. This is right off the table. And the concentration of O plus is 7 millimoles. And then in the ECF, it's 10 and 70. So when you look at the concentration X plus, right? So here's my container, right? And so inside the cell, because I don't need a container, X plus is 120. This is for X plus. And outside, it's 10. So there's more ions inside the cell than outside the cell. It's actually a 12-to-1 concentration. So if I opened a channel for X plus, so here's my cell, right? And we have a large X plus on the inside and a little X plus on the outside because the concentration is small. If I open a channel for X plus is going to diffuse out of the cell and go into the extracellular fluid, right? And as it leaves the cell, we're removing positives from the inside, so that makes the cell more negative. Okay, so I know the equilibrium potential sign is going to be negative for X plus. Right now, they can never both be negative or both be positive. So you said, okay, if I did that right, then X plus has a negative equilibrium potential sign. I would expect the O plus to have a positive one. Let's kind of draw that. So again, here's my container. Here's my cell. From the table, we can see inside it's 10 millimoles and outside it's 70 millimoles. So we see that for O plus, we have 70 outside and 10 inside. Okay, so if I draw my cell, I have 70 outside, which means I'm going to get, a big O plus outside, a little O plus inside. I open a channel and the O plus diffuses in. As O plus diffuses in, we're taking positives from outside to inside, and the inside becomes more positive. So it is, in fact, as we expected, my equilibrium potential sign is positive. Now, actually, in this case, the equilibrium potential signs were given in the table, but it's kind of a good way to figure things out. So that confirms what we had, and if it wasn't given, then we could tell from the information we had for those things. All right. We also want to know, just again, this is given, what's the percent permeability at rest? And these are the only two ions we have to worry about. So the table gives me 95% for X plus and then 5% for the O plus. And then percent permeability at peak is 10 and 90. Percent permeability at hyperpolarization is 98 and 2. That's again off, all this is off the table. And the equilibrium potential, we know that we figured out it's negative for X plus, and the number, the magnitude is given as 100, and it's positive 100 for O plus. So remember, it's not the sign of the ion that matters exclusively. Yeah, it's going to play a role in determining whether the equilibrium potential sign is plus or minus, but it's actually the direction that it moves as well, and what happens to the inside of the cell as whether or not you determine the equilibrium potential sign. Okay, so that was given, and so now we have all this information from the table, and we can calculate the information we need given that. So I'm going to start with a new page. All right, I get those ads because this is a free app. And I don't know how useful it really is, so I don't know if I want to pay for it, but it seems to be working fine now. So let's look at it. So the first thing we want to do is we want to calculate what the resting membrane potential is going to be. So how do I calculate the resting membrane potential? Well, the resting membrane potential, we are given some information, okay? So we know for X plus, we know a couple things at rest. We know the equilibrium potential equals minus 100. We also know that the percent permeability at rest, let's say percent at rest, is 95%. So I have to put that in a decimal form, so that's 0.95. And so that was given on the table as well. So for O plus, because we have to know both ions, we have to know the contribution of each ion, the equilibrium potential sign and magnitude was positive 100, and then the percent rest was given as 5%. And here's a common mistake that students sometimes make on this problem. Say, oh, 5%, it's 0.5, right? Actually, you have to divide 5 by 100, which is 0.05, right? So the 5% is 0.05. And these two should add up to 1.0. If they don't, then somewhere you messed up, right? Because these are the only two ions and their contribution should add up to 100%, okay? So I want to use the general formula. The potential equals the percent permeability times the equilibrium potential plus the percent permeability times the equilibrium potential. All right, so this would be for ion A, and this would be for ion B. So we're just going to say A, right, it's going to be this one, and B is going to be that one. All right, so now I'm just going to replace the numbers. All right, so for X plus, right, I get the percent permeability, 0.95, times the equilibrium potential, negative 100. That equals negative 95, plus, it's probably easier just to stack them up, I think. So for O plus, I'm going to go 0.05, that's up here, times positive 100. Now, oftentimes we don't write positive or negatives when we're doing math, right? I mean, sorry, we don't do positives, we do negatives, but we just assume the positive. But I think for these problems, it's probably a good idea to make sure you include it so you don't drop a sign. So always make sure you have some sort of sign there. So that's going to be positive 5. So if we add those two together, minus 95 plus 5, that's going to give me minus 90. This is, again, millivolts as given the problem. So I can figure out the peak. Sorry, this is rest. So this is rest, minus 90 millivolts, and that's my resting membrane potential. All right. I think it's easy to just do all of them while we're doing this because it's really the same problem, but all we have to do is change this part. Right? So the equilibrium potential doesn't change at all for the given scenarios. All it changes is the percent permeability of the two ions given the situation, whether it's rest or peak. And in this case, we actually have hyperpolarization. So I'm going to do this one in blue. I didn't want that. So I'm going to do this one in blue. So X plus equals, and then from that table, if you remember, was 10%, so 0.10 times minus 100 equals minus 10. For O plus, that equals 0.90, so 90% times positive 100, and that equals positive 90. And together, that equals, I believe, positive 80 millivolts. And this is at peak. So I just took the same equation and applied the percent permeabilities given at rest, and then for the first one, and then for peak for the second one. And now, given this problem, actually, if you look at the table, it gives you the hyperpolarization. So we're going to do that as well. So X plus equals 0.98 times minus 100 equals minus 98. And O plus equals 0.02, right? So that's 2%. So you've got to divide that by 100, so 0.02. Again, those two add up to 1.0, so we're okay. That's times positive 100, so that's positive 2. And if I add those together, I get minus 96 millivolts, and that's the hyperpolarization. So those are the values that we need for rest, peak, and the hyperpolarization. Again, you don't always get hyperpolarization, but if it is there, then you can easily calculate it. And basically, we use the exact same equation, right? This equation, again and again and again. So if you don't know how to apply this equation, you're not going to be able to do this problem. And in fact, you can't do the last part of this problem as well. The last problem says, well, we need to figure out what the threshold voltage is, okay? So threshold voltage is a little more complicated, and it involves a couple different steps. Okay, so I want to figure out what the threshold voltage is. And in this problem, and most of the problems, it's given as 10% of the difference between peak and rest, okay? And so the way we do that is, first of all, we want to figure out what the total excursion is. And for the total excursion equals the absolute value of rest plus the absolute value of peak. So if we start at rest at minus 90 millivolts, we have to move 90 units to get to 0. And then peak is at plus 80, so we've got to move 80 more units. All right, does that make sense? To get to peak. So together we move 90 to get to 0, and then from 0 to peak, we move another 80, so that's 170. Well, the easiest way to do that, right, is just take the absolute values. So the absolute value of rest at minus 80 plus the absolute value of peak, oh, sorry, rest was minus 90, sorry, minus 90, plus 80. Basically, for the absolute value, you ignore the signs, right? That's going to give me 90 plus 80, and that's going to equal 170 millivolts. So my total excursion is 170 millivolts, okay? So that's step one. Step two is now I want to take the percentage of that. And in this case, it's 10%, or 0.1, that's 10%. And you can see that in the problem when it says something to the effect of, at a given point in time, when it receives enough excitatory input at 10% of the difference between rest and peak, the channels start to flip-flop. So that's the definition of a threshold. So the channels that were open, the X plus, begin to close, and the channels that were closed, the O plus, begin to open. So the percentage is 10% or 0.1, and you take that and multiply it by, so you get the percentage times the total excursion. So in this case, I get 0.10 times 170, that equals 17 millivolts. But I'm not done yet, because that's how much I have to move from rest to get to threshold. So number 3 is move that many units from rest towards 0. So if you were starting at a negative voltage, you would go in the positive direction. But if you had a positive voltage, you'd go in the negative direction. So you'd subtract it. But in this case, since we're already negative, we're going to add. So we get 90, right? Plus, we're going to add 17, right? So, sorry, minus 90, because we're negative, right? Plus 17 is going to give me minus 73 millivolts, and that's going to be the threshold. All right, so there's 3 steps. You got to figure out the total excursion first. The easiest way to do that is take the absolute value of rest plus the absolute value of peak. Then you take the percentage of that total excursion that was given in the problem. In this case, and in most cases, it's 10%. So 0.1 times the total excursion of 170 gives me 17 millivolts. Then I start at rest and move that many units towards 0. In this case, I start at minus 90. That was my rest, right? So if you look up here, right, there's my rest right here, minus 90. And so I add the 17. That's from here. This is from that. And I get minus 73 millivolts. That's my threshold. So we'll look at some other components of that as well. But that's the way to do the math portion of the action potential problem. And for number 8, it asks for the schematic of the efferent fiber system. So that's comparing the somatic and autonomic nervous system. And basically what we want to do is we want to include the sympathetic, parasympathetic, and somatic. So this is a written description of it, but I think really this is the best way to look at it. Let me see if I can figure this out. Okay, so I've displayed the schematic and made it so that you can easily see it, so we can kind of go through the major points to it and get that done. So for the somatic nervous system, it's something you probably already know a little bit about, especially from anatomy. It's our voluntary motor control unit, right? The cell bodies for the neurons, right? Generally speaking, they're found in a couple different places, your cerebral cortex or the ventral gray horn of the spinal cord. Okay? These consist of fibers that are beginning, their cell bodies are in the CNS. They exit the CNS and go out to the periphery. So there's not a ganglion that is associated with these. Okay? They're just single fibers. They go to the end organ. In this case, because it's voluntary, the end organs would be skeletal muscle. And they release the neurotransmitter acetylcholine, so we say ACH, to cholinergic receptors. Remember, any receptor that responds to acetylcholine is going to be a cholinergic receptor, and the subtype is nicotinic. So these are nicotinic receptors. So pretty simple somatic one. The sympathetic and parasympathetic are a little more complicated. The sympathetic nervous system is known as fight or flight. Sometimes it's known as the thoracolumbar area because the cell bodies initially arise from the thoracic and lumbar area of the spinal cord in the lateral gray horn. So in the thoracic and lumbar area of the spinal cord, you have an extra horn. Now the one that goes in the front is called the anterior gray horn, and the one in the back is called the posterior, or sometimes they're called, ventral and dorsal. But in areas where there's the sympathetic neurons, there's an extra gray area of the spinal cord, which primarily houses cell bodies, called the lateral gray horn. So those are found in the lateral gray horn of the spinal cord. They have a short preganglionic, so they go in a ganglion. So the first fiber is called preganglionic. The second fiber is called postganglionic. All right. Now that's was opposed to the somatic nervous system that's called non-ganglionic because it doesn't go with the ganglion. It goes from the CNS directly to the skeletal muscle. So this goes into a ganglion. A ganglion is a collection of cell bodies in the peripheral nervous system. Okay? So the synapse releases acetylcholine to cholinergic receptors that happen to be nicotinic. Okay? The second ganglion is called the postganglionic fiber. Now, in the sympathetic nervous system, the preganglionic fibers are very short. They exit the spinal cord and almost immediately go to a ganglion typically. That's called the paravertebral ganglia, sometimes called the sympathetic chain ganglia. And there are some that go in front of the spinal cord called the prevertebral ganglia. And again, these fibers are really short because they exit the spinal cord and immediately synapse somewhere else. Okay, so they go to those chain ganglia especially, and then those go out to the periphery to wherever end organ it is. The end organ could be cardiac muscle, smooth muscle, or glands primarily. So it could go to the heart, it could go to small intestine, it could go to a sweat gland. It could be any of those out on the periphery. Now those are a little more complicated because we have a different neurotransmitter that's typically released in this area, okay, and that's norepinephrine. Now, the receptors that we have are called adrenergic receptors, and adrenergic receptors respond to adrenaline. Now, adrenaline is known as epinephrine scientifically, and it has a close relative which also excites these receptors called norepinephrine or noradrenaline. So that's where the adrenergic name comes from. Now what's interesting is, what's interesting is that we do have a receptor on the presynaptic membrane. Okay, so remember this represents a synapse in this area right here. And so this side is called the presynaptic membrane, and over here we have the postsynaptic membrane. And generally speaking, the receptors occur on the postsynaptic membrane. But in the case of the adrenergic receptors, we have a special receptor called an alpha-2 receptor that's on the presynaptic membrane. And its job is to prevent the excessive release of norepinephrine. And this gets again to those receptor properties we've hit again and again and again: specificity, competition, and saturation. And what happens is if you have a lot of norepinephrine release, then you're going to saturate the receptors on the other side of the synapse, on the postsynaptic membrane. And once I get close to saturation, it doesn't do any good to have more norepinephrine. And so we would want to limit the norepinephrine release once we got towards that area. So these alpha-2 subtypes have a low affinity for norepinephrine, meaning they typically don't bind norepinephrine until you get to a high concentration. So if we have a high concentration norepinephrine, that binds to the alpha-2. And what the alpha-2 does, it serves as what's called a feedback inhibitor. It prevents the release, or at least slows down the release significantly, of norepinephrine. So what it does is it keeps us from having to release it when it doesn't do any good, because I already have enough of it in the synapse. If I release excessive norepinephrine, I have to replace that. I have to make that, and that takes a lot of time and energy physiologically. So it's better to control the release, and that's what the alpha-2 does. It prevents us from over-releasing norepinephrine through feedback inhibition. The other receptors are known as alpha-1, beta-1, and beta-2. While technically not part of the exact question asked, we might as well talk about them. Alpha-1 are the most common ones, and they're found pretty much everywhere. They're what give us the normal sympathetic response. And except for the exceptions that we've mentioned before, and I'll mention in a minute, for the betas, it's an alpha-1. So as an example, I've never mentioned what the receptors are on a sweat gland, and that's because it's an alpha-1. And so where I want you to know about alpha-1s specifically is in blood vessels in the systemic system. And stimulation of an alpha-1 receptor in a blood vessel in the systemic circulation causes vasoconstriction, right? And we're going to hit that when we get to the next section. That's why I want you to remember that one. Now, the beta ones, so that's the second one, the beta one. The beta ones are found also in the heart primarily. There's also some in the kidneys. But in the heart, what it does, the beta 1s, is it speeds up heart rate. It makes heart strength contraction stronger, and it increases the conduction velocity through the heart. So those are beta 1 receptors. And if you've ever heard of like a beta blocker, right? A beta blocker is a drug that slows down heart rate. And what it does is it blocks the action of beta 1 receptors. And so if you don't have beta 1 activity, which speeds up the heart, that's going to slow down the heart. So beta 1 receptors increase the strength of contraction, increase the conduction velocity, and increase the heart rate. So those are too easy. It's too easy to say that scientifically. So we have to have these fancy scientific names. Okay. So beta 1 receptors have what we call a positive chronotropic effect. So positive means increases, and chronotropic means heart rate. So beta 1s have a positive chronotropic effect. The second one is inotropic. So a positive inotropic effect because it increases the strength of contraction. For those of you that have to take pharmacology later, or you might be even taking it now, sometimes they talk about a class of drugs called the inotropes. Those are the drugs that increase the strength of contraction of the heart. So if someone had some sort of like heart failure, they would be taking an inotropic drug to increase the strength of contraction. And then the third one is that they have a positive dromotropic effect. So dromo refers to conduction. So a positive dromotropic effect would increase the conduction velocity through the heart. So the actual electrical activity would go faster through the heart. All right. So as a quick summary, right, not all, we'll see the exception in a second, most of the sympathetic fibers are characterized by a short preganglionic fiber arising from the lateral gray horn. It releases acetylcholine to nicotinic receptors. In the pre- and paravertebral ganglion, the cell body is located in the pre- and paravertebral ganglion. For the postganglionic fiber, that tends to be a long fiber that goes to the end organ, which is typically cardiac muscle, smooth muscle, and glands. And that releases norepinephrine to adrenergic receptors on the presynaptic membrane called alpha-2 that only get activated in high levels of norepinephrine release. And it also releases it to adrenergic receptors on the postsynaptic membrane called alpha-1, beta-1, or beta-2s. Now, the exceptions to this rule are fibers that go to the kidney and the adrenal glands. Okay? Now, the adrenal glands sit on top of the kidney, right? Sometimes, as a matter of fact, now there's a push to call them the suprarenal glands, so above the kidney, basically. But still, they'll be called the adrenals probably forever. Just make more work for you having to know both names instead of just one. These don't go through a ganglion technically. They actually go to a ganglion-like cell in the organ they go to. So these also start in the lateral gray horn. They go out to the end organ, in this case the kidney or the adrenals. And the only ones I want you to really know are the adrenals. And what they do is they have chromaffin cells. And chromaffin cells are in the adrenal medulla. So a quick review of organs. The organs can have two areas. The outer area is called the cortex, and the inner area is called the medulla. For the adrenal glands, there's the adrenal cortex releases a number of different hormones. We'll talk about some of them later in the different zones. So you have the zona glomerulosa, fasciculata, reticularis, if you remember that from the adrenal glands. We're not concerned about those today. We're concerned about the inner part called the medulla. The medulla has these special cells that stain darkly called chromaffin cells. And the chromaffin cells release epinephrine. So that's the key. So anytime we have sympathetic stimulation, we're going to stimulate chromaffin cells in the adrenal gland to release epinephrine, which is going to help support that sympathetic stimulation. So you should understand that exception. And then the last one is the parasympathetic. That's called rest or digest. I also said feed or breathe sometimes I use. It's the craniosacral also, because these arise from the brain and the sacrum part of the spinal cord. So instead of getting too fancy, we're going to say these cell bodies are found in the brain and the sacrum, right? So cranial is brain and sacrum makes sense. These are kind of opposite what the sympathetic fibers do for the most part. So instead of having the short preganglionic that the sympathetic does have, these have a long preganglionic typically. So this exits the brain or spinal cord in the sacrum area and go directly to the end organ. And so that's why they're long. Okay. There is a ganglion on the end organ. There's actually usually multiple ganglia. These are called in general terminal ganglia because they terminate at the end organ. So you still have that connection, but this doesn't occur until you get to the organ. So that's why you have a long preganglionic. And then since we're already at the organ, the postganglionic fiber is really short. So that's opposite. So it's called terminal ganglia in general. And we release acetylcholine to nicotinic receptors. So what makes this kind of easy is let's go back and kind of look at the first synapse. So here, for the somatic nervous system, there's only one synapse, right? Because they're not ganglionic fibers. And we release acetylcholine to nicotinic receptors. We come up here to the sympathetic system, and we see that our first synapse is acetylcholine to nicotinic receptors. We didn't talk about it, but not surprisingly, the synapse here at the chromaffin cells is acetylcholine at nicotinic receptors. You don't have to know that, but it is. And then for the parasympathetic, it's acetylcholine to nicotinic receptors. So the first synapse is always going to be acetylcholine and nicotinic receptors. Okay. So for the terminal ganglia, right, their postganglionic cell bodies are in the terminal ganglia. They are short axons, and they release acetylcholine, but this time to muscarinic receptors, so a different type of receptor here at the end organs. And muscarinic receptors do whatever the parasympathetic system does, and the thing I want you to remember is they're antagonistic to the beta-1 receptors. So beta-1 receptors were in the heart. That's the main place we're going to worry about them. So we're going to worry about the muscarinic receptors in the heart, and they have opposite or antagonistic effects. So we had the heart rate increase, the strength of contraction increase, and conduction velocity increase at the beta-1 receptor with norep and efferent stimulation. So these are going to be the opposite. So we'll go with the scientific term and explain it. The muscarinic receptors have a negative, because it goes down, chronotropic effect. They decrease heart rate. The acetylcholine to muscarinic receptors have a negative inotropic effect, slight. It decreases the strength of contraction, not very much, but a little. And then they also have a negative dromotropic effect. They decrease the conduction velocity through the heart. So that's kind of an overview of the schematic of the efferent motor system, comparing the somatic with the sympathetic and the parasympathetic.